Hi everyone, just wanted to take a minute to talk a little bit about the last of the conic sections, parabolas, which are probably the ones that prior to this year you would have had the most encounter with. Mostly because these are the graphs that you are getting with just any old quadratic, right? These are the kind of the U-shaped, right, that we solved before, and we were dealing with like factoring and completing the square and quadratic formula and all that stuff. So you've seen this before. Now we are going to take this into the scope of the conic section world, which means a lot more vocab and kind of an explanation of where it comes from. Now, some of the numbers and things that you might look at and go, why is that like that? Now, if you do go through the process of the distance formula and completing the square and things like that, you can see a little bit more clearly where they come from. But before we start, I do want to say that the word origin of parabola is quite literally from the Greek meaning application, because this was found as an application to solving problems relating to area. So if anybody ever asks, remember the word quite literally comes from the Greek for application. And again, the curve, the bolo in Greek, I think has something to do with curving too as well. So it makes sense in that regard. So again, once again, just want to point out means application. So ha. Now, moving on. The parabola, that is the set of points that are going to be the same distance from a given point, which again, we are dealing with the focus here. And this other line that we call the directrix. I'm not exactly sure why it's called the directrix. Um, I didn't look that up, to be honest. But regardless, before with the circle, right, we had the center and we were saying these are always the same. Then we had the ellipse where we said, okay, this plus that was the same. And we had the hyperbola where I said this minus this was the same. But now we have that this and this are the same. So this is equal to this. Now you'll notice this is always perpendicular. So if I go like that to that, that's the same distance, which is nice. It's kind of it's a nice way of graphing it and looking at it. And it kind of, again, keeps that idea of these constant distances in play that we've been dealing with in terms of the rest of the conics. So it's kind of a nice way to relate them. Now, here's kind of what we need to know. Here's the general overview of info. Um, we can have vertical parabolas, which are the ones that you're most familiar with. That's the ones in the form, the y equals, and then you have the x squared. But you can also have horizontal ones. These are the ones that are not functions. They look kind of like that, or like that, kind of the two hyperbolas, if you will, or the hyperbola. And then we have the axis of symmetry, which we've seen before. That's the segment that you could kind of reflect it over. It helped us with graphing. Then we start getting into the focus. Now, if we go back to our focus here, you'll notice the focus is within the curve and the directrix is below the curve. And they are the same above as they are below. And the reason behind that, as you can see here, is we know that all the distances are the same. So if it's this distance up, it's that distance down. And that particular distance comes from the 1 over 4a. So again, if you want to see where all that work is coming from, I implore you to kind of go through the process of the quadratic formula, but it does relate, or the completing the square and things like that, where you get the force in the a and when you take the square root. But anyway, that's where it comes from. It comes from the 1 over the twos and things like that. But ultimately, these are the pieces of information that are going to help you. There's also this concept of something called a latus rectum, which means straight side in Latin, which is this line up here. And it has a length of 1 over a, absolute value. It's just another way of kind of rationalizing and looking through some of the information, and can provide you some of the info about a, which is going to be helpful for you. In terms of application components, I'm not really sure of what the latus rectum is providing you. But it's neat to know, and it's good information to provide you with information about A, right? Because if it's 1 over A, oh, well, I can figure out what A is. So let's take a look at something like this. First and foremost, we need to figure out what this is in vertex form. So we're going to do my personal favorite of complete the square. All right, so let's take a look. Well, I'm going to factor out the 2 because I don't like it. X squared plus 6x. Now, I'm just going to leave it like that, over plus 14. If it makes you feel any better, what you can also do is kind of like divide everything by the 2 and then subtract the 7, put it over here. You're going to ultimately multiply it back in anyway, but that sometimes helps people kind of visualize it and figure out why I'm doing this process. Now, again, we're going to do the 6 over 2 squared equals 3 squared, which equals 9. So I have y equals 2 times x squared plus 6x plus 9. Now we're doing that to get the perfect square trinomial in here, but we have to keep it balanced. Remember, if I'm adding 9 here, I'm not actually adding 9. Remember, I'm adding 2 times 9. Now normally we would add it to the other side, but because we're dealing with just one side, we'll just subtract it. So this is minus 18. 2 times x plus 3 squared minus 4. Now, we can clearly see that my vertex is going to be -3, -4, right? It is the same on the outside, opposite on the inside. This is opening up because my A is 2. So A is 2, so it is opening up. Right? If it's positive, it opens up. If it's negative, it opens down. Now, obviously, if you're dealing with x and y switched, positive opens right, negative opens left. And then we have, what's the other thing it's asking me? Oh, axis of symmetry. So the axis of symmetry is going to be going through, if you look at it on a graph, it is going to be x equals -3. If you kind of take a look here, right, what do we have going on? We know the axis of symmetry is x minus h when it's vertical, or y equals k. I'm sorry, not minus. X equals h in vertical, or y equals k in horizontal. All right. The only thing you have to be careful of is when it is horizontal, you have minus k and then plus h on the inside and the outside. So they do kind of switch. Right. So here's one, for instance, where it will switch. So let's take a look at it. Well, we have 3x. I'm going to move the y over there. Y squared plus 8y plus 31. Well, let's complete the square. Okay, well, that's going to be 8. 8 divided by 2 equal to 4. Square it. Squared equals 16. Y plus 4 squared plus 31 minus 16. So I get 3x equals y plus 4 squared plus 15. Now I divide by 3 because I don't want that like that. So divide by 3, divide by 3. So my equation then will be x equals 1/3 y plus 4 squared plus 5, which makes my vertex, this is now h and this is k, 5 minus 4. It is going to be opening to the right because a is positive. And my axis of symmetry, right, it's kind of the thing on the inside, so it is y equals -4. All right, so just remember, the thing on the inside is your axis of symmetry. Now, you can find out the equation of the directrix and things like that if that helps you. For our purposes, it's not necessarily looking. These are annoying numbers, and the fact that we have a of 1/3, so your directrix is going to end up being a little bit of an annoying equation, right? Because you have it's horizontal, so it'd be 1/4 times 1/3. So it'll only be what, 3/4. But anyway, next thing. Let's do another one. All right. Name the coordinates of the vertex and focus, the equations to the axis of symmetry, and the directrix. So, let's see, what do we got going on? Oh, the length of the lattice rectum. And then graph. All right, let's do this. Well, I want it in the form x equals or y equals, but y appears to be squared, so I'm not going to touch that. So I'm going to move the x around. So I guess first we're dividing by -4. So I have x minus 4 equals -1/4. Sorry. Y minus 8 squared. I'm going to add 4 to both sides. X equals -1/4. Ooh. Y minus 8 squared plus 4. So my vertex appears to be 4, 8. Okay, so over 1, 2, 3, 4, up 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. Here, 8. It is opening left because that is negative. Okay, so it is going to open left. By the way, it's kind of wide, so remember, it's a fraction, so it's going to be wider. Now, what's my next thing it's asking me? Axis of symmetry. Okay, so my axis of symmetry is y equals 8. Here's my axis of, let me put that in a different color. Here's my axis of symmetry. Boop, 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 boop. Okay. Direction of opening, left. What is my directrix? Well, let's ask ourselves, how do we find the equation of the directrix? I'm going to put this in purple. Okay, so the directrix, when it is like that, it is going to be x equals, x equals h minus 1/4 times a. All right, well, let's ask ourselves, what is h? H is 4. Okay, minus 1/4. A is, oh god, -1/4. Oh, actually, that simplifies nicely. Okay, 4 minus, that's -1. So 4 plus 1, which is 5. Now, the nice thing to know is that you know this is outside of it. So if you kind of had no idea which way it opened, if you know it's to the right over here, right, here's my directrix over here, you already know it's going to go the other way. Which also, by the way, does mean that I'll put this foci here, the foci would go over 1 as well, because it ends up being plus instead of minus. So there would be the foci. Now, my lattice rectum is, how do we find out? The absolute value. I already did pink. All right. Lattice rectum. Absolute value of 1/a, which is the absolute value of 1 over -1/4, which is 4. Right? So that means, well, my lattice rectum would go through here and it would go up like that. 1, 2, 3, 4. So it's going to scale kind of like that. And then, so that would mean it would look kind of like this. Right, so it'll be wide. And you can keep plugging in points if you want to, but ultimately it's going to kind of get that general shape going there. But it's very wide. All right, so there's that one. Um, that's pretty much everything that you would need to focus on for this. If you get something like this, where you get the vertex and you get the focus, um, first and foremost, right? Plot what you have. You go over 1, 2, 3, 4, 5, down 1. Then you go over 1, 2, 3, down 1 for your focus. So you already know it's going to go this way because you know the focus is kind of within the curve. Um, so you already know it's in the form x equals, a y minus k squared plus h. So x equals a y plus 1 squared plus 3. Now, we also know that the focus is at 3, -1, um, which means how far up did I go? Oh, well, I went over 2. All right. And we know that the focus has the coordinate of h plus 1 over 4a k. So, the -1 doesn't change, but the h will, right? We know h is equal to 3, so 3 plus 1 over 4 a equals, oh, sorry, that's a 5. 5 equals 3, right? You subtract, I get 1 over 4a equals -2. So 1 equals -8a, so a equals -1/8, and so on and so forth. So you can go through that process. All right. But it's ultimately kind of the same for all of them. The important thing to note and to be honest is just be able to write this down so that way you can get the information to be able to graph them. All right. Once you get all the general information, it's really just kind of connecting the dots. All right. Let me know if you have any questions and have a great day.